Hello, and welcome back to my videos on calculus. Today we are going to begin by talking about limits. Now, if you are, learning calculus for the first time, you have likely not had any experience with limits before, or at least you don't think you have. In many Algebra 2 and many pre-calculus problems, they have problems similar to that of a limit, but they don't tell you that it's a limit. In this video, I'm going to be talking mostly about the conceptual idea of a limit while using some examples, some very basic examples, and I will talk about certain properties of limits that might be useful. The limit of f of x, where f of x is any function as x approaches point A, where A can be any point in which we are taking the limit, is defined to be L. And this is the mathematical definition of a limit. This definition here, it's not the formal definition of a limit, but it will suffice for our purposes here today. This is how you would write a limit. For example, if we want to know the limit as x approaches 2 of x squared, what we would do here is try to imagine the points getting close to 2. Now, we'll do that for another example in which it'll be easier for me to demonstrate what I'm trying to demonstrate, but for this we could just plug in 2 for x, and 2 squared is obviously 4, so the limit equals 4. Now this works for the general case where you just plug in the value of a for the limit and you just get the answer. However, usually limit problems will be a little bit more complicated than that. You won't be able to just do that. You might have to do some algebraic manipulation, which I will talk about in just a moment. But what you need to consider here is that we don't care about what the value is at the limit. So we know that 2 squared equals 4. That's true. But we don't actually care what the value is at 2 squared. We care what value it's approaching. Now we can prove using formal mathematics, using proofs, using something called the delta epsilon definition, which I won't talk about right now because, I'm only trying to give a general definition of the limit. The epsilon delta epsilon definition comes in handy later on, but it's not necessary right now. But there is a mathematically rigorous way to prove that the limit actually is 2. However, since this is just really an introduction to calculus at this point, we're only going to consider proving it using algebraic methods. F of x seen here is an example of a hiccup function, and the reason it's called a hiccup function is because it looks like a hiccup when you see it on a graph. So you can visualize this graph as imagining a line along y equals 3, because y equals 3 for all values except for when x equals 3. When x equals 3, the function hiccups to 5. So the value is 5, and for that one point, it is not along the line y equals 3. But for the rest of the function, it's at y equals 3. So it's called, so it hiccups to that point, and that's why it's called the hiccup function. Now we can imagine taking the limit of this function as x approaches 3. Now, the limit as x approaches 3 of f of x. And f of x is clearly defined up here. So now I want you, as the viewer, to take a minute and think about what you think the answer to this will be. Okay, good. So now I'll assume you have thought about it for at least a few seconds, and some of you might have come to the conclusion, come to the right answer, especially if you, know a little bit about limits, but some of you might have come to the answer, x, it's 3. I'm sorry, it's 5, because when x equals 3, the answer is 5. However, we only care about the value that the function is approaching. The function is approaching 3 for all points, because for every point other than x equals 3, it's approaching 3. And it's still approaching 3 as x is approaching 3, y is approaching 3. So the value 5, the value y equals 5 for x equals 3 has no consequence on the limit, because all the limit is concerned about is what value you are approaching. So the answer to this is 3. Now, the problems we have been working with have been fairly simple problems, and the reason for this is because I wanted to get across the concept of what a limit is to you. And I hope I have done that, well, to a sufficient amount, to a sufficient degree. And now I think I will talk about some properties of limits that may be helpful in the future. One very important property of limits is this. This indicates that we can factor a constant out of a limit. So if you have a constant here being multiplied by a function, for example, if you had 3 multiplied by x squared, then you can simply factor 3 out and multiply it by the limit. Then you can take the limit, get the result, and then multiply it by the original constant, as shown here. These 3 properties of limits are all very similar, and they're all very fundamental. And they're also very intuitive. So we can take the limit of a sum or a difference, and all we need to do is take the limit of the individual parts to get the limit of the whole. The same thing goes for multiplication as well as division. Now let us consider a slightly more complex problem. We have the limit as x approaches 2 of x squared minus 7x plus 10 divided by x squared minus 4. And you'll see here that if you simply try to plug in 2 to this function, then what we have is 2 squared equals 4 minus 4 equals 0. Now, we cannot divide by 0 in mathematics, so we're going to have to manipulate this a little bit to make it solvable. So, what is normally required in a situation like this is factorization, is to factor this back into its original form. And you should know how to do that from algebra. And it's a very useful skill to have when working with polynomials, such as the one in the top left corner of your screen right now. So the factorization, and I'm not going to do this right now, but I'm not going to do it out, but I know that the factorization is, and you want to make sure, just for consistency, to rewrite limit. The factorization is, in the numerator we have x minus 2 multiplied by x minus 5. And in the denominator we have x minus 2 multiplied by x plus 2. And you can see immediately that this is a much easier problem to work with than this. It's the same problem, but we factored out both sides, both the numerator and the denominator, and we can see that x minus 2 is in both the numerator and the denominator in our newly factored form. So we simply canceled that out, and we're left with the limit as x approaches 2 of x minus 5 divided by x plus 2. And now we can simply plug in 2 for x. So we have 2 minus 5, which is negative 3, and 2 plus 2, which is 4. So our limit is negative 3 divided by 4. You'll notice this last problem was a little bit more difficult, and it was not as trivial as the examples that I was using in the beginning of this video. Well, limits, many limits require manipulation similar to what I did in the previous problem, and sometimes you multiply it by 1, meaning, maybe you could try multiplying by x minus 2 both the numerator and the denominator. That works sometimes. There are many neat tricks you can use, but you generally have to reason a lot of these out. However, many limit problems are the same, and in mathematics, well, practice is essential. to becoming good at calculus and any branch of mathematics. So if you practice limits long enough, then many of these problems will have similarities, and well, you'll be able to do them. You'll be able to work with them much faster, and it'll just be more efficient. Now, in my next video, I'm not going to introduce new concepts. I'm simply going to work with some limits problems and work them out on the board, on the whiteboard, and hopefully this will give you better experience, so that when you have to solve limits problems, or when you have maybe you have a test coming up, or maybe you're just interested, but you'll be able to do it well, just as well.